Hello learners, welcome back to the course on deformation processing of materials. In the previous lecture, we had seen the advantages and disadvantages of forging process. We saw the relation between the force and height to which the hammer is raised. We also saw the effect of friction on the forging force, and after that we had seen the open and closed die forging processes, and towards the end we had seen various forms of forging operations, and with that we had concluded our discussion on forging. So today, now let us begin with bending and stretch forming operation. So this is a sheet metal forming operation. Okay, so we have bending and stretch forming. Stretch forming. So these are very simple operations carried on sheet metals to give them required or desired shapes. Okay, so let us begin with the schematic directly. So this is something like, say we have dies like this, which are used to bend the blank. Okay, so we have the die like this, and from here we can have the bent blank. This will be something like this. This is too much. So like this, we can bend the sheets. There will be strains on both the sides, but this will not be same in any case. There will be there may be very slight difference, but they will not be exactly equal or same. Okay. So this angle here is known as the half of the bending angle. Okay. So this angle is alpha. Okay. And this is our blank. This is the die. Also, I mentioned that the strains E1 and E2 will not be equal. Okay. So always there will be some difference. Always there will be some difference. And let us see which kind of shapes will be formed here. Okay, so suppose we have initial blank of thickness Ti. So we will denote this initial thickness as Ti, and shapes like cones, missile cones, etc., or conical domes, etc., can be easily formed using this process. So shapes like this can be formed. So say this section is like this. So conical sections like missile cones, etc., can be formed. So Now let us see some relations, as we have seen three things here: alpha, E1 and E2. So there are two relations, one with alpha and other with E1 and E2, which are the strains. So if we take the section, taking the section, what we have, so say after forming, we are taking some section of the formed product. So here, as I mentioned earlier, this angle will be alpha, which is nothing but the half bending angle. Okay. And this thickness now becomes TF. So there are two relations. First one is sine alpha is equal to the ratio of this final thickness TF to the initial blank thickness. Okay. Here, let me write that initial thickness is the blank thickness, and final thickness may be sometimes written as the cone thickness also, okay, or TC. So these two are basically the same. So this is the first relation that we have. Okay. And there is one more relation with the strains, that the initial thickness to final thickness, this ratio is equal to e raised to power E1 and e raised to power this epsilon 2. Epsilon 1 and epsilon 2 are the strains, or we should say are the true strains. Okay. So here alpha is half bending angle, half bending angle. Okay. Ti or Tb are the initial thickness, and Tf or Tc are the final thickness. Okay. And E1 and E2 are the true strains. And E1 and E2 are the true strains. Okay, so let us quickly see very short numericals based on these two relations. Basically, there is a numerical problem which has two parts. Okay, so say in the first case, we are given with a missile cone with final thickness of the sheet or formed cone as 1.5 mm, and its half angle is given to us, the half angle of the cone, and that will be nothing but the half bending angle only, because cone would have been bent at the apex itself. Okay, so we have missile cone of thickness equal to 1.5 mm. Okay, so say this is cone thickness is 1.5 mm. This is given to us. Okay. Again, the half cone angle is alpha, it is given as 30 degree. 30 degree. This would be the profile of cone like this, and say this is the angle alpha here. So we need to find the blank thickness required for forming this kind of conical shape with the given thickness. Okay, so we need to find the blank thickness. So with the first relation itself, we can uh, find the blank thickness. Okay, so we have now, we had sine alpha as TF over TB. Okay, so applying that, sine of alpha is TF by TB, and we know the value of TF and alpha. So this will be sine 30 degree is equal to TF or TC are same as I have mentioned earlier. So this is 1.5, and TV we need to find. We know that sine 30 is 1 by 2. So this is 1 by 2 equals to 1.5 over TV, and this becomes TV as 1.5 into 2, which gives us TV as 3 mm. Okay. So in this way, we have determined the thickness of blank required to form a missile cone of thickness 1.5 mm by bending process. Okay. So similarly, let us see the second part of the numerical, where we are now given with the initial thickness or blank thickness and the true strains that will be developed at the two ends of the blank. And now we need to find the final thickness which will be achieved in this forming process. Okay, so here we are given with TB as 1.5 mm. Okay. And say we had the blank like this. This is the schematic representation. So like this, and say here the strain was 0.05, and here it is 0.09. So now we need to find TF. Let me write more clearly. TF we need to find. So in this case, we can use the second relation which we had seen, which was the thickness of blank divided by thickness of cone or final thickness is nothing but e raised to power epsilon 1 into e raised to power epsilon 2. Okay. So for this, the solution will be, you know that TB over TF is e raised to power epsilon 1 into e raised to power epsilon 2. And if we substitute the values, we have here 1.5. TF we need to find e raised to power 0.05 into e raised to power 0.09. And these values come out to be, say, this is 1.051 and this is 1.094. Okay. So solving this, this becomes nothing but 1.144. Okay. So from here we can find TF as 1.5 over 1.144. Okay. And this gives us TF as 1.311 mm. So using that second relation, we have found that if the initial blank thickness was 1.5 mm and the true strings developed at 0.05 and 0.09, then in that case the final thickness which will be achieved is 1.311 mm. Okay. So now let us see an important concept related to the bending operation. So we will now see the bending allowances. Basically, in the bending process, uh, in most of the metal forming processes, we have seen that elastic recovery takes place. So after the forming operation, when the load is removed, the material recovers to some extent due to the elastic recovery. Okay. So that happens in the case of bending also. So suppose we have bent a blank like this, and after the removal of load, it would regain some of the strain or deformation, or it will again move towards its initial shape to some extent. So in that way, we need to consider that elastic recovery also, and for that we provide the bend allowances in case of bending operation. Okay, so let us see bend allowances. So for better visualization, let me draw a schematic first. Then we will see the relation for bend allowances. Okay. So suppose we have a sheet which is being bent. So say this is a sheet. Let me draw more clearly. So this is like this. Okay. And it has some thickness like this. Okay. So it is say like this, and in the cross section this extends like this. This line will extend to this point. So we can see that it has been bent. So, like this. So here there are some terms which are related to this geometry. So say the width which is being bent is B. So this width will be B, and if we consider the thickness to be T, then this is the thickness. Thickness is T. Okay, and here we will have bending starts from here, so like this, and it ends somewhat here, like this. So say this is the center line. Let me use some other color. Let us use this. Like this. Okay. So if this is the center line, we will be this has erased everything. Let it be. Okay, so here this will be the bend radius. Okay. This. What happens? Okay, so this is the bend radius R. Okay, and this angle is the bend angle alpha, and here there will be the allowance that we are talking about. This is denoted by B. So this is denoted by B. This is the bend allowance. We'll see with one more schematic that how it is important. Okay. So this was to demonstrate what are various things which we are talking about. Okay, so here R is the bend radius, and B is the bend allowance, and alpha is the bend angle. So let us now see after bending what happens to this. Means how the spring back is important, because spring back or elastic recovery will lead to some recovery in the dimensions. So to, if we have to suppose reach to some dimension or bending extent, say uh, this much, then we need to bend this much, and after it will means this much will be the allowance, and it will recover this much, and finally we'll get this shape which we want. Okay, so let me draw another schematic, and then we will see the relation for bend allowance. So if I see the uh, front view of this particular schematic again, and then we consider the spring back, then how it appears is, say this was our sheet. So say this is the final shape we want. Okay, so this is something that we want. Like this. And in order to achieve this, we will need to bend it a little more. Okay, so let me represent by that by dotted curves. Okay, so in order to achieve this, we need to bend this material like this. Okay. And it will be like this is a little bit thicker, so why it is becoming so like this. And this was the actual thing. So solid line shows the final dimension or final bending that we want to achieve. Okay. And this dotted line shows the actual extent we need to go so as to achieve the desired bending. So in this case, there will be two bending angles. Okay. So let us denote the dotted one by R naught. Okay, so here this, say for this dotted one, say the radius will be little bit shorter. Okay, so this is R naught, and for this solid one, the radius will be little bit longer. Okay, so this is say RF. Okay, this is the final radius of curvature that we uh, bend radius that we want, that is needed to us. Okay, and these angles will be now for this. We know that the angle will be alpha f, because this is the final desired thing. And for this one, for this angle will be, see here, when the radius is low, the angle is high, and when the angle is high, the radius becomes lower. Okay, so this will be alpha naught, and this shows the spring back in bending. This schematic represents the spring back which happens in bending process. Okay, so considering this, the bending allowance or bend allowance is given as bend allowance is given as nothing but, it can be written in terms of both the initial radius and the final radius. Okay, so this is nothing but R naught plus T by 2 times the bend radius, sorry, bend angle in case of this. Or if we consider the final bend radius, then in that case, what will happen? We will replace both the radius and the angle by final values. Okay, so this is RF plus T by 2. This is appearing like T, so this is F. Okay, times the final bend angle. This is an important thing to consider in case of bending forming operation. So this is the relation for bend allowance. Okay. So this considers the elastic recovery or spring back happening during the bending process. Now let us see the various forms of bending operations carried out. Okay. So depending on the shapes which are needed, there are various forms of bending operations. Okay, so we will now see various bending operations. Various bending operations. So the very first one is simplest one, the channel bending. And as the name suggests, this leads to the final cross section, not the cross section, actually the final shape as a channel. Okay, so we have channel bending. So what happens in channel bending is, we will see all these with the help of schematics only, and that will be very clear. Okay. Means, say we had the initial shape like this, and this will be now converted to channel like this. So this is nothing but channel bending. Similarly, we have Next one is the U bending, and this is very clear from the name that the final shape will be U, U kind of shape. Okay, like alphabet U. So again, initially we had this shape, so this will be now formed into or bent into. This is initial, and this is formed into U shape like this. And for this, punch shape like this is used. Definitely to achieve this section, a U-shaped punch will be required like this. Okay. So this is the punch. Similarly, V bending is done. Okay, so in V bending, again, the shape will be like alphabet V. So we have V bending. In V bending, we have, say, this is the initial one, initial blank, and this is bent to a V shape like this. It will be more sharper, say like this. And in this case, a V-shaped punch will be used. So this is like this, V, and a punch, something like this is used. So this is the punch in case of this V bending. And there is the next one is the offset bending, where a double V type of shape is formed. So next one is known as offset or double V bending. Okay, so next we have offset or double V bending. Double V, double V bending. So this is also very simple. In place of a single V, there will be two V shapes. So suppose this is the initial one or blank, and this is transformed into a shape like this. So here we have formation of two V's like this. So suppose this goes like this, um, like this. What happens to this? This is the double V or offset bending. Now, next one is the edge bending, and as the name suggests, uh, the blank will be bent at some edge, and a section like L shape will be formed. Okay, so next one is the edge bending. Okay, so here what happens is, suppose we have the initial blank like this. Okay. So it is transformed into a shape like this. It is bent at uh, the edge of some die. So how is it done? So say there is some support like this, and the blank is kept like this, and there is a die which bends it from this edge. Okay, so say like this. So this gets bent in the form of given shape. Again, there are some operations which are carried on this sheet metal. They are basically not bending. They may be categorized into the punching or means forging type of process they are, but we will keep them here for simplicity. Okay, so next one is blanking or punching. They are basically forging type of operations in which press or punch is there, which pushes or presses the sheet metal. Okay, so next one we have blanking or punching. Blanking or punching. They are basically the same operation, but based on the final product form, we give them the names blanking and punching. So suppose there is a die onto which the blank is kept. So since we are using red color for the blank, so we'll follow the same. So suppose we have the blank like this, like this. Okay. So it will be pressed using a punch. Okay, so say this is the punch. Like this is the punch. And it will cut down the section from this blank. Let me draw this a little smaller like this. So this section of the blank will be cut with this punch. This section. So it is like this. So this will be cut out. Okay. So there will be dies at the bottom which will support the blank. Say like this. This is the die onto which this blank has been kept. And after the punch passes from here, the cutout part will be dropped at the bottom like this. This is like a thin coin. You can assume this actually coins are made by this process only. Coin type of shapes etc are made by this only. Okay, so how this is called blanking or punching? This part which has fallen out determines that. Okay, so let me write the names first. So this is our punch and this is the blank. This is the die. Okay. So if this part is useful, this part is uh, useful, means this punched out part is useful and remaining blank is of no use to us, then in that case this process is known as blanking. And if this is discarded, So if this is discarded or scrapped, discarded or scrapped, then in that case this is known as punching operation. So this determines whether it is blanking or punching. Similar kind of operation is there, which is known as piercing. And piercing is the process of making very small diameter holes into blank or sheet. Okay, so as the name suggests, it pierces into the blank. Okay, so next one is piercing. This is the process of making small holes. Making small holes. So let us see the schematic for this again. So we have again the dies. Like this. In case of piercing, blanking, punching, etc., dies are kept a little tapered at the bottom side from where the cut out part or punched out part falls, because they act as an allowance for it to fall down. If it were straight, then after blanking or punching, the punched part will be stuck into that cavity or portion. Okay, so these dies are or the holes are slightly tapered towards the bottom section, uh, like one shown in this schematic. Okay, so on this the blank is kept like this, and a very sharp punch is used to draw the hole, to punch the hole out here. So like this, there is a punch which is very sharp, and it pierces a hole here. Okay, so this is a very sharp punch, very sharp punch. This is the blank, and this one is the done. This is the process of piercing. Now the next process is, actually these are not bending or stretch forming processes. These are a separate class of processes, but since we had not discussed them, we are keeping them here. Okay. So these are a sort of forging operations, because here we are using punches like we were using in case of forging. Okay, so this next one is nibbling. Nibbling is the process of engraving or writing on the sheet. Okay, so writing on the sheet. On the sheet, and here nothing but small holes are drawn onto the sheet, so that joining together it appears like some engraving or some letters or alphabets or any writing like appearance comes on this. Okay, so suppose we have the blank like this. This is, say, the top view of the blank. Then we will have engraving on this, like, okay, so let me write it like this. Say this is, say we are writing a word leg on this. Okay, so this will be like this. And if you zoom or magnify it, and then observe, then you will see that this is nothing but a combination of very small holes like this. So it is formed by these holes. Like this, they have been joined together. I have drawn them very far, but they will be much closer. So they appear as a complete letter or word or anything which is drawn over there. So this is something like this. Like this. Okay. These are overlapping holes. One means they overlap with each other and form the complete word. So these are overlapping holes. So this process is known as nibbling. Next operation that is done is notching, and again very obvious from the name that in this process notches are created onto the material. So this is notching. So simply a notch like this will be formed onto the component. So this is the process of notching. Next one is embossing. And in embossing, there is some impression onto the punch, and when it is pressed against the sheet or the component, the engravement gets or impression gets transferred onto the sheet. Okay. So next one is embossing. So suppose we had again a sheet or blank like this, and onto this, suppose a shape like this has been formed. Let us make any shape, say a star, like this. Okay, so basically the punch will have this impression. Okay, so the punch has this impression. Okay. For example, if we emboss the symbol or emblem of any organization onto any component, say signboards or anything, nameplates, etc. Okay. Metallic nameplates, etc. So, for example, embossing the logo of an organization. Logo of an organization. So this is known as embossing. Next process is coining, and it is an extended form of embossing where both the punch as well as die will have the impression, and the impression will get transferred to the blank on both the sides. In this way, the coins are made. You must have seen coins which have impression on both the sides. Okay, so coining process is adopted where punch and die both have the impressions. So next one is coining operation. So in coining, both punch and die have impressions. So both punch and die have impressions. Okay. And again, this will be a similar arrangement which was used for that blanking operations. So let us see the cross section. So suppose we have die like this. Onto this, the blank is put, and the punch presses it from the top. Like this. So in this way, coining is done. So this is our punch. This is the blank, and this is die. So these were various forming processes till blanking. Means before blanking, the processes which we saw were bending or stretch forming type of processes, and since these were left out, so I have mentioned them here. So these are basically forging type of processes. Again, these are sheet metal forming processes. So blanking, punching, piercing, nibbling, etc. we have seen now. Okay, so for carrying out these operations, uh, the force required can be determined. So let us see that only. Okay, so this is an say extra note here. That force required for blanking or punching. This is an extra note. This is not related to bending or stretch forming, remember. So force required for blanking or punching. Required for blanking or punching. So this is simply given as the total length which is being blanked out, means the perimeter of the punched out part into the thickness of the sheet metal into the shear strength of the sheet metal. Okay. So this is the relation here. L is total length, perimeter of punched out part. T is the thickness. Okay. And tau is the shear strength. Okay. So by this relation, we can find the force needed for carrying out the blanking or punching operation. Okay. So let us quickly see a short numerical based on this relation. Okay. So in the question, suppose we are given with the dimensions of the punched out part. So suppose square section was punched out. So here, say these are 20 mm by 20 mm sections. Okay. So this is 20 mm, 20 mm, and this is again 20 mm. So this is a square section, and the shear strength is given to us as 350 megapascals. Okay. 350 MPa. Also, the thickness is thickness is 2 mm. Thickness is 2 mm. Now we need to determine the force required for blanking or punching this part. Okay. So find force. Let me write it in the line here. So find the force F required for blanking or punching. Okay. So simply we have to substitute the values. Here the trick is to find the perimeter. We should not directly put 20 as the length. Okay, so here the force is given as L into T into tau. Since tau is given in megapascals, so if we put the length and thickness in mm, area means the product will be mm square and MPa is nothing but Newton per mm square. So directly it will get cancelled out and we will get force in newtons. If we convert the shear strength in pascals, then we need to put the dimensions in meters. Okay, so keep in mind the units while solving the numerical problems. Okay, so this is the length will be 4 times 20 because here we need to consider the perimeter. Okay, so 4 into 20, thickness was 2 mm and the shear strength is 350. Simply we have to take the products. So this is 80 into this becomes 700. Okay. And this again becomes 56,000 newtons, or more simply we can write as 56 kilonewton. So this much force is required for. See, only 20 mm section is being punched out or blanked or means punched or blanked, and for that we require 56 kilonewtons of force. So the shearing or means this blanking or punching operation is not a joke. Basically means this much high forces are required here. So again we have reached towards the end of this uh, blanking or punching operations or left out forging operations. So now we have seen today the bending or stretch forming operations and then blanking, shearing, piercing, etc. Okay, so let us close for now, and in the next class we will see the some of the high energy rate forming processes. Okay, so we are now very towards the end of this course. Basically we have covered almost all the conventional processes. These are some advanced processes which we can consider as these are being explored nowadays. Okay, so let us see them in the next class. Thank you.